Now modifying this, I had got the value of ln A, that is ln k1 plus t2 ln k1 minus ln k2 t1 minus t2. Now the rate constant can be calculated by above equation, okay, and the energy of activation can be calculated by this equation. I am having two equations, one to calculate rate constant and the other one to calculate energy of activation. Moving forward, now we'll see what data we are having. The level of impurity in stability study at 40 degrees centigrade is 0.24 at 3 months time point. Similarly, at 30 degrees centigrade is 0.10 at 3 months time point, and the initial level of impurity was 0.05%. The specification limit of the impurity is 0.30%. Now the rate of the change of impurity per month is equals to the level of the impurity at defined time point, that is at 40 degrees centigrade it is 0.24% minus initial level of impurity divided by time point. So for 40 degrees centigrade it will become 0.24 minus 0.05, that is the initial level of the impurity, divided by 3 is equals to 0.063% per month. Similarly, for 30 degrees centigrade it will 0.10 minus 0.05 by 3 is equals to 0.016% per month. Now the data we have is initial level of impurity is 0.05%, specification limit of impurity is 0.30%. Rate of the change of impurity at 40 degrees centigrade is, that is what K1 is 0.063%. Rate of the change of impurity at 30 degrees centigrade is K2, that is 0.16%. Temperature, now here you have to add 273 degrees always, because we usually measure temperature in degree centigrade, but in this equation you have to equate temperature in the degree Kelvin. So you have to calculate for 40 degrees centigrade it will be 313 degree Kelvin, and for 30 degrees centigrade it will be 303 degree Kelvin. Universal gas constant, that is R, will always be constant for 1.987. Moving forward for this, now putting above details in equation number 9. Now we had already seen the equation number 9 is EA is equals to RT1 T2 ln K1 minus ln K2 T1 minus T2. Now we are having all values here we had seen, so all values we had equated, and we had energy of activation for the product is 25157.44. now that is for product, energy of activation is for product. Similarly, rate constant can be calculated by equation 12. So ln A is equals to ln K1 plus T2. Here we had calculated energy of activation. Now we will calculate for rate constant, and the rate constant is 37.6911. This we had calculated with our equation number 12. So now we are having rate constant for the product. Here we are having energy of activation for the product. Now as we had calculated energy of activation and rate constant, this can be put into the Arrhenius equation at 25 degrees centigrade, that is at 298 degree Kelvin, to estimate the shelf life of product. in long term condition. For this, here we calculate first the rate of the change of impurity at 25 degrees centigrade with Arrhenius equation. That is what I was talking about, that rate of the change of impurity at 25 degrees centigrade. Now we are not having data of the rate of the change of the impurity at 25 degrees centigrade, but we can calculate it with the data what we are having for 30 and 40 degrees centigrades. We are having the value LNA, that is the constant, which what we have calculated just 37.69119. So this we had equated. So we had equated it over here. We are having rate constant, energy of activation, what we have calculated with equation number 9. We had equated it here. We are having the value of R, that is gas constant. We had equated it here, and obviously the temperature, that is at 25 degrees centigrade, so 298 degree Kelvin. Now we can calculate with this the rate constant, that is rate of the change of impurity per month for 25 degrees centigrade. So now the rate of the change of impurity per month at 25 degrees centigrade will be 0.008267% per month. Moving ahead, as we know, the specification limit of the impurity is 0.30. Now the specification limit of the impurity is 0.30, which we have set already in our specifications. Rate of the change we are knowing, initial level of impurity we are having, so the shelf life will be of the product will be specification limit of the impurity minus initial level of the impurity divided by rate of the change of impurity. The simple calculation, and you can understand that 0.30 minus 0.05 divided by rate of the change of impurity per month, that is what we had calculated just now. And solving this equation will get the shelf life of the product, that is 30.24 months. So going back to our presentation, we had seen that we are having two data sets, one is at 30 and one is at 40. How we had equated the equations and calculated the rate of the change of impurity per month. For shelf life calculation, if we are knowing the rate of the change of impurity per month, we can calculate it for the shelf life. So the shelf life of a product is equals to the specification limit of the impurity minus initial level of the impurity divided by rate of the change of the impurity per month, and that we have calculated 30.24 months. Now limitation of the above calculation is all erroneous calculations for shelf life estimation are not considering humidity factor. So now, for example, if we are knowing that our impurity is responding for humidity also, then this could not be giving us correct estimation of our shelf life, but it can be used as a tool to really understand and to really make decisions at the critical level where we require the help of mathematical tool to know the behavior of the product or to anticipate the behavior of the product. But this method will help definitely where we are knowing that our impurity is temperature dependent or is very sensitive to temperature and is responding to temperature very much. So moving ahead to this, thank you guys.